As the initial hurdles of unmanned robotic platform development have been passed, focus is now being placed on advancing the behavior of these platforms so they perform coordinated operations in groups without human supervision. Considerable amount of work has been conducted in this area under various names such as swarming, network systems, cooperative control, and multi-agent systems. The premise behind multi-agent systems is that cooperation among group members can lead to the execution of complex functions. Formation control is an important problem in multi-agent coordination and cooperation. Here, the objective is for agents to form a prescribed geometric shape in space. This requirement is intrinsic to tasks such as area coverage, perimeter protection, and co-transportation of large objects. A popular method used in formation control attempts to regulate a set of inter-agent distances to prescribed values. In this method, the main concern is convergence to the desired spatial configuration, irrespective of its global position in space. That is, the formation is acquired up to rotation and translation of the whole set of agent positions. As a result, this method is inherently decentralized, since it can be implemented in each agent's local coordinate frame. Some interesting ambiguities arise when employing this method. For example, how can the control distinguish this formation from this one? How about this formation from this one? Or this one from this one? Well, let's see how the distance-based formation control framework can deal with these ambiguities. To deal with the first ambiguity, it is convenient to use rigid graph theory. Now, notice that both of these structures or graphs have 4 vertices, but each one has a different number of edges. From our intuition, we can see that the structure on the left is not rigid like the one on the right. The two-dimensional structure on the right is said to be rigid because it has at least 2n-3 edges, where n is the number of vertices. That is, we need at least 5 edges to ensure that a structure with 4 vertices is rigid. To demonstrate the concept of formation rigidity, the following experiments utilize 2 wheeled robots that are controlled to form these virtual structures. Each robot represents a vertex, while each of the virtual edges are inter-robot distances that are regulated by the formation control algorithm. We will refer to the control algorithm being demonstrated as distance-only control. The direction of the edges indicate tracking directions. Robots 2 and 4 are tracking their distance from robot 1. Then if agent 1 is moved along an arbitrary direction, the formation controller forces the follower robots to maintain the desired distance. There is no regulated distance between 3 and 1. Therefore, we see that the virtual structure becomes visibly distorted. To avoid the distortion, we can add the 5th edge between agents 3 and 1 to ensure a rigid structure. And now, when agent 1 is forcibly moved along a similar trajectory, the follower agents actively regulate their respective inter-agent distances, and therefore the virtual square formation is maintained. So now we have a way to ensure virtual rigid structures. Unfortunately, that doesn't help us solve the ambiguities related to orientation and flips. In the next set of experiments, we demonstrate how the initial conditions can affect the performance of the distance-only formation controller. In the first panel, agent 4 starts below the imaginary diagonal line intersecting agents 1 and 3. Then once agent 4 moves towards the bottom left corner, the desired formation is acquired. However, if agent 4 starts above the diagonal line, it will attempt to converge to a flip position that still satisfies the inter-agent distance requirements. Fortunately, this undesired behavior can be resolved by including another controlled variable in the formation control algorithm. Here, we use the signed area of a triangle as the additional variable. The signed area is calculated using this determinant-based formula, where p sub I denotes the 2x1 position vector of vertex I. The signed area is positive if the vertices are ordered counterclockwise, negative if ordered clockwise, and 0 if any 2 vertices are co-located or 3 vertices are collinear. If the formation involves more than 3 robots, the formation graph can be triangulated and a signed area defined for each triangle. Therefore, by using inter-agent distances in conjunction with the signed areas in the control algorithm, the desired formation is acquired even when agent 4 starts above the diagonal. In summary, the distance-only formation control method suffers from the local nature of its stability properties. However, its stability can be made almost global by first ensuring the formation graph is rigid, and then introducing an additional feedback variable, such as the signed area, in the control law.